All right. Anyways, what we didn't quite get to yesterday was actually filling these out, but we were using that moving man simulation. Still, we're on one axis moving around. Before we jump right into this, I don't care about the review questions for right now. Let's just jump into the main part. Interpreting position graphs, or sometimes position time graphs, more specifically. Um, just some general questions before we start. If something is moving with a constant velocity, what general type of graph will you see? Okay. Linear, good. Linear means straight line, right? What's the only type of straight line you cannot have in reality for this application? Yes, vertical. What did we say the issue with that was? If we have a vertical line on a position time graph, why, not mathematically, but why conceptually doesn't that not make sense? Yeah, exactly. You can't be at a bunch of places at the same time. But anything else linear-wise is possible. Any linear line, other than that one, represents some kind of constant velocity motion. Then where we kind of got just cut off at the end, just starting to talk about acceleration. And the two forms, I know there's three, but the two forms that we could undergo on a linear axis is speed up and slow down. If they're speeding up or slowing down, either form of acceleration, what kind of general shape do you see? What you say yesterday? Go ahead. Some kind of curve, some kind of parabolic curve. Might not be a full parabola. Most of the time, probably not, unless something we talked about a little bit later happens. All right. So technically, if acceleration in general, it doesn't have to be parabolic. It could be a crazy curve, like a weird function curve. However, in this course, we're limited to algebra and don't use calculus. Because of that reason, we always only study uniform acceleration. And with that, you want to learn more about that as the weeks go on. With uniform acceleration rates, it's always nice sweeping parabolic curves. Okay? So with all that stuff in mind, some of these questions, we're all going to do just about all of them together, but some of them are like more specific than others. All right? Some of them are more vague and like several answers could still be a right answer. Right? We'll mention that as we go. Some of them are much more specific and like only one particular graph is going to answer it correctly. This is going to be your study guide for the assessment on this stuff. I'm not calling it a quiz because here's my plan before we get started on this. I think I mentioned yesterday, we are definitely getting the subscription to physicsclassroom.com, but I don't know exactly what day it'll all be processed. If we finish all this graphing stuff in the next couple of days and we get our login information for that, then you're going to do like graded for correctness concept builder since it'll be able to track your work. That's going to be like your quiz, but you're going to be allowed to have all this stuff open. All these study guides could have that be right in front of you. If for some reason we're not there yet and can't get on those concept builders to track your progress, then I'm going to give you some kind of like quiz version, like an open book quiz, okay, basically, where you could have all these out in front of you. So make sure you do these right. When it's all said and done today, when we finish this, sometime before tomorrow, I want you to upload this just to get a few participation points. Even though we're doing it together, when you finish this, upload it to the assignment you got it from. You'll get like 3 points for having it completed, okay? All right, so let's get started. So in number 2, there's 2 lines we got to draw on each one. We'll label them A and B. Probably should use different colors so it looks nicer. So line A in the first box up here just says remaining at rest. All right, describe a line to me that would just simply mean this object is at rest. That's how we started yesterday with the moving guy thing. Go ahead. Good. It has to be horizontal. Technically anywhere horizontal, right? So it really doesn't matter where we draw it starting from on the y-axis as long as it's horizontal. I'll put it up. Oh, I'm on the eraser. Hold on. So label it line A. Any horizontal line will do right there, though. Now, for line B, this is pretty general. There's a lot of different answers you could give that are correct. Because just saying a thing is moving, that's not very specific, is it? It doesn't say moving constant speed. It doesn't say a direction. It doesn't say if we're speeding up or slowing down. So there could be many right answers to this one. But for consistency purposes, let's all write the same one. Describe me a line of something moving. This is definitely at rest, so it can't look like this, right? Can't be horizontal. But give me an example of a line that would represent moving in any way, shape, or form. What kind of line could I draw that satisfies that? Morgan, a slanted line. As long as it's not pointing straight up, right? We could draw any slanted line. Let's draw it like, I'll use a different color. Let's draw it something like that. I could have drawn it slanting down. I could have even drawn a curved line, right? All those would be moving, right? So that's a pretty open statement for B. Anything that's moving. All right. Yesterday I kind of did something like this next one. If you have any questions at any point, say something before I move on. Moving slow and moving fast. So for graphical purposes, you really can't tell if something's, slow and fast is a relative thing, right? So we have to have two graphs when we're talking about identifying graphically if something's slow or fast. But this was one specific one we went over yesterday. How would I draw line A as opposed to line B? We gotta consider both at once. If line A is supposed to be slow and B is fast, yeah. I think you did it with your hand correctly. More. Right. Okay. So steepness. Okay, or the slope. More the mathy term slope. Right. So let's just refer back to the at rest line. If a slope of 0, that's what this would be, right, is at rest, then a slope a little bit more than 0 would have to be slow, wouldn't it? Still almost flat, but can't be flat because it wouldn't be moving, right? So basically a less steep one for A and a more steep slope one for B, right? Because in the end, when we're talking about constant velocity, if we're drawing linear lines, we are. The slope of the line, which at the very end of the fact we'll find exact slopes with numbers. The slope of the line is the velocity on these things. This one has a greater slope, higher velocity, moving faster, to a lesser slope, the one that's closer to 0, right? So as long as B is slope greater than A, anything like that will do. These ones are pretty general too. Moving a positive direction, moving negative. I'll still draw it constant and linear, even though technically I could draw it curved because it doesn't say speeding up, slowing down, or constant, right? So we'll keep it as basic as possible for now. Moving in the positive direction, that way's positive, right? Positive slope. Now notice something on this. It only gives us a quadrant 1 to draw on, doesn't it? All right. But we did say yesterday for a lot of these graphs, a quadrant 4 could be possible. Because we could have negative positions, right? If this is the origin. But why did we say quadrant 2 and quadrant 3 over here for these types of graphs wouldn't be possible? Wouldn't be reasonable. Yeah. Right. Times on the x-axis, anything in quadrant 2 or 3 would be negative times, and that can't happen, right? But since we're stuck only in one quadrant, because that's all they gave us, we have to answer it, satisfy the line in one quadrant. So moving in the negative direction would look like this. This is line A, this is line B. Now, just because you're moving in the negative direction, though, do you have to be in the negative position values? No. All right? You just have to be moving towards negative, right? Down here is negative. Here's 0. These are all positive numbers on the y-axis. These are all negative numbers if there was a fourth quadrant, right? So to be moving in a negative direction doesn't have to mean that you actually currently hold negative values. You're just going towards values that are. Does that make sense to everybody? All right? You could be in the negatives and maybe more negative too. But you don't have to be. The point is you're moving towards more negative when you're moving in the negative direction. When we're moving positive, we're moving positive. If we had a fourth quadrant, we could have drawn a positive direction one starting down here, right? So we move towards positive. All right, now we're going to start getting a little more specific. A little more. So line A down here in this one has to be moving at a constant speed. Again, we started the class with this. Constant speed means that your line has to be what kind of line? Any kind of line that is what? Yeah. Linear. Any linear line. Even a flat one, well, of course, not vertical. Any linear line that's not vertical, even a flat one, that's stopped, but isn't staying at 0 meters per second? a constant speed, right? So it could even be flat, but any linear line that's not vertical. So I'll just make one like that. What did we say about acceleration before for line B? Some kind of what? We don't know if it's speeding up or slowing down, so it's not that specific. But whether it's one or the other, it's what type of shape, basically. Not going constant if it's accelerating, right? Those are two like opposite things. Go ahead. Curve, some kind of curve. Let's just draw one that maybe looks like this right here. Some kind of parabola, partial parabola, any kind of curve is going to represent some kind of acceleration. The exact kind, we're getting to that. We good so far? Okay, now we got to focus on what type of acceleration and the direction it's occurring in. So, with parabolas and partial parabolas representing speeding up and slowing down, we could kind of relate it, even though these were linear, to this one. Higher slopes mean going faster, right? So a curve, line A has to represent speeding up. So a curve that represents speeding up has to get steeper as time goes on, all right? Not flatter. So, and more specifically, we also have to be going in the positive direction. Which way is the positive direction? Going upward, right? So we have to get steeper and going upward with a curve. That locks us into really it has to be a line that looks like this. Going upward and getting steeper as time moves on, right? That would represent moving in the positive direction and speeding up. Line B is moving in its positive direction, so we still have to sweep up but slow down. We can't get steeper. We got to get less steep or flatter, closer to zero, right? The only way to do that with the curve would be to go like that, wouldn't it? We're still going upward to the positive direction, but this curve started steeper and got more flat, didn't it? So that would represent what line B wants us to put. Any questions on that one? Very similar, but now we have to speed up and slow down again, but we're moving in the negative direction in this box, right? So we have to sweep downward while speeding up or slowing down. So the only way to move in the negative direction or towards the negative direction and speed up is to go something like this. It needs to get steeper downward, right? The steepness increases downward. That would be line A. Moving in a negative direction and slowing down, we'd have to start somewhere up here, go towards the negative, and flatten off. Get closer to flat at least. We'll move on. Does this make sense? All right. The bottom two on this page really is just another way. The bottom two on this page and going on to the next two on the next page are really some of these same exact graphs, asking it in a different way. So I need to review something real quick before we go to these ones, something we already learned. Like I said, all kind of stuff builds on each other in here. Stuff from the past, you'd almost expect at some point it's coming back somewhere. Right? So when we first learned about acceleration, day one of it, I gave you a little example where I said I saw a vehicle that you guys didn't see, and it had an acceleration of -5 meters per second squared. And I asked you, does that have to mean it's slowing down? What was the answer? Yes or no? No. We gave examples why. You got to know which way it was going in the first place and kind of cross-reference that with the direction of the acceleration. So we made a little chart, and I told you to write on that study guide or write somewhere when we did that. It was a chart that said if we had positive V and positive A, positive, same sign means speeding up, right? But if we had negative V and negative A, that also meant speeding up. Remember that? And then we said if we had a negative V and a positive acceleration, since they're opposite signs, that's slowing down, or vice versa. If we had positive V and negative A, that's slowing down. They're basically asking me in these next four the same questions here, but making you remember that. They're not going to use the word speed up and slow down. They're going to use that sign connection. We got to remember that and get it right. If we remember that, it's easy, and we could point it out that it's going to match one of these four and these two up here. All right, so this one starts off positive velocity, positive acceleration. That means the same as speeding up in the positive direction. So really, since that means the same as that, we already did that one. This one said moving positive, direction speeding up, right? So that statement right there is another way to say this right here. We got to realize those two mean the same thing. If they mean the same thing, then the graph would look the same. So this graph down here looks exactly the same as the graph up in this one, graph A in this one. If you want to note it in the margin, what this information tells me is that it's speeding up because of the plus and the plus, right? The next one, we're moving with the positive velocity, so we got to go in the positive direction again, but a negative acceleration. Those are opposites. That sign and that sign are opposites, so that's got to represent a slowdown acceleration. But we're still sweeping towards the positive because the original velocity is still positive, right? So we got to be moving upward while doing this. That's how it flattens off. So that would be like line B in this one, right? So the description of line B in this one, that statement right there, means the exact same thing as that. Everybody with me? All right, flip on to the back. The second page. Same idea here. Two separate signs. Negative velocity, positive A. Slow down. But this time we are sweeping negative. A negative velocity means the direction we're traveling in. And we got it slow down while moving towards the negative, so this one has to look like that. And that would be, if we flip back, that would look exactly like this line B in this graph, just set in a different way again. Moving negative direction and slowing down. And the final one's going to look like this line A, because it's the same thing, just negative, negative. Same signs, simple same signs there and there. That has to mean speed up. Speed up while we're going with a negative velocity to begin with, so that would have to be a downward steeper trend like that. Basically, just be familiar with both ways of saying those two things. They don't have to say the word speed up and slow down. They could imply them by giving you the signs. Now, we're just going to flip what we just did now in the next couple questions. Instead of, here's a description, give me a graph. Here's a graph, give me a description. These boxes are small, so we're going to keep it as brief as possible, okay? But there's two segments in each one, so here's what I'm going to do to keep track of it. I'm going to write segment 1 by the first part, and then there's a dot, and there's a segment 2. So we're going to describe each separately, okay? So be as specific as possible, guys. For segment 1, being as specific as possible, what is going on right here? Give me a verbal description. What could we say is going on with segment 1? Got it, Amy? Very good. That's everything right there. It's slow. It's linear, so that means constant velocity, right? And it's slope, positive slope, so that means positive direction. So let's just write that as short as we can. Constant, I'll abbreviate that. Constant, positive velocity. Segment 2, this should be an easy one. What happened in segment 2? It's horizontal. What does that mean? Or somebody else. It's a horizontal flat line mean. Yeah, go ahead, sir. It's at rest. Or stopped, or whatever you want to say. Good. We all good with that? Alright, the one to the right of it. Segment 1, segment 2. And we'll do like a comparison one here. On this one. So we can. Notice something we did on another one. What could we say about segment 1? At the same time, since they're both linear as well, let's kind of give a comparison answer as well of the two. Segment 1 compared to segment 2. What could we say? Which one's moving faster? Right? 2, because it's steeper, right? So let's say for segment 1, they're both linear, right? And they're both slope positive, right? So segment 1, constant, positive velocity, but all right, slow, because we could compare it to a little bit of a faster one, right? So segment 2 would also be a constant, because it's linear, positive velocity, but this one's a little faster. Slope greater, right? And I mean, just to throw it out there in general, everything we're saying here, of course, is specific to a position time graph, right? But you could apply this stuff to all kind of other instances. All right, anything you're graphing, whatever rate you're talking about. Our rate happens to be a velocity because we're talking about something in motion, right? But if you have a graph of anything, it doesn't have to be a position time graph, and one line is sloped greater than the other, that means something about that line is occurring more quickly than the lower slope line, right? And moving down to the bottom left. Segment 1. What could we say about segment 1? Be as specific as possible. Obviously a curve, so look at that. In general, a curve tells us acceleration, but what kind, guys? What is happening to this curve? Is this curve causing speeding up, or a result of speeding up or slowing down? Okay. Speeding up, yes, why? Right, it's getting steeper, right? So, and it's going positive, so we could say a positive acceleration, specifically speeding up. Segment 2, we speed up to a certain point, and now we're back to a positive constant linear, right? We have this one. Positive constant velocity. So it looks like we sped up to a point, then maintain that speed. This is something you do in a vehicle often, right? You're at a stop line at a stop sign. Turns green, you hit your accelerator, you speed up. You don't speed up forever, right? I hope not. You speed up for a while, and then you reach maybe like the speed limit, right? Nobody goes beyond speed limit in here, right? And then you stay at that until something happens, right? So that would be representative of like 2 segments where something like that might occur. So positive constant velocity again there. Most we could say about it. Sometimes this bell ring, I always forget. Go be playing. Alright, finally the last box on this one. Segment 1, it's a curve. We have acceleration. So what kind? Right. It's decelerating, which means slowing, also as a way to say slowing down. It's getting less steep. It's moving in the positive direction, but it's slowing down because it's getting less steep. Slowing down in the plus direction. And in segment 2, it slowed down so much that it actually came to a stop, right? Completely flattened out. If a lower and lower slope of the curve flattens out, then we completely came to rest. So this one's at rest in segment 2 again because it's flat and horizontal. Any questions on those? All right, since it didn't give me one, you don't just pay attention. You don't have to write this. I'm going to go to a blank sheet for a second. Just eyes up here real quick. It didn't give me any full parabolas to discuss, did it? But that's a possibility, so let's discuss those on a PT graph. Just pay attention. What if I had this? What must have happened to an object that did something like that? It's a full parabola, not just a part of one. Okay? You're right. You're definitely not wrong. So I'm going to add one more extra big point there. It slowed down and sped up again, but it changed direction, didn't it? Because this half of the parabola is going towards the negative, right? this half goes up to the positive. So if I'm the person that the object is moving, matching this graph, well, a couple things. This graph didn't start at the origin. So let's make my number line here. Let's say the corner of my desk is the origin, okay? That way's positive, that way's negative. I clearly started at some positive position, right? Away from the origin. So that must mean my motion began, at least we started tracking the motion somewhere over here. Make sense? Some positive number. And I was going towards the origin. I didn't get there though, did I? So I was slowing down as I was coming towards the origin because it's getting flatter, right? But then, math word, vertex. The vertex of a parabola applied to PT graphs is where you would have to do what for a moment before you turned around. You can't turn around 100% the other direction without doing what for at least a moment there. Stopping, right? I have to stop. Even if I do it very quickly, I have to stop for a brief moment, right? So I stop for that brief moment at the vertex, and then I start going back in the positive direction, right? So this is sweeping positive, but as I do it, I get faster and faster and faster because it's getting steeper and steeper. So a parabola, a full parabola in any form, represents on a PT graph you turned around. You slowed down, turned around, and got faster. It could also go like this. The only other kind of full parabola could go like that. This would mean we started like near the origin, in this case, slowed down going away from it in a positive direction, then came back towards it faster. And you guys should know that you can't have sideways parabolas from math because those went past the vertical line test, and we'd have the similar issues with sideways parabolas, that there would be some points where you were like it's saying that you're in two places at once, which is impossible. So those are the only possibilities for turning around fully on this stuff. All right, last part. Oh, I didn't mean to do that. Here. All right. So we've been saying the whole time the slopes of these graphs, especially the linear ones, the slopes of these graphs represent the velocity, right? So now that we have graphs with numbers, we can find the velocity knowing how to do elementary slope, which we should all know how to do. So here's what I'm going to do. I'm going to do one of these with you guys, since we're a little low on time. I'm going to do this top left one with you. You're going to finish off the other three and then submit this by tomorrow, okay? But like any graph with finding slope, you want to use two nice points, right? If this was full grid paper, that would be points that hit the corner of a box, right? If possible, we do that. So if we look at this one, first given one, we could use the origin. It looks like it starts from there. That's a nice point right there, right? And the very end point, we can see it hits right on a perfect dot, right? So let's use those 2 points. And like we would typically do in, like, way back in middle school, this would be easy stuff. Give me the points, the origin 0, 0 for this one, right? And this point would be, looks like 5, 20, right? Now in generic math, you would call this point x1, y1, right? And this one x2, y2. But we're not so generic right now. We don't have just an x and y axis. We have a position and time axis. We've named them. It means something more specific, right? So we can still think of it, if it helps, as x1, y1, x2, y2. But the y's are actually positions, the x's are actually times, right? But you're still going to do the same, and I'm going to put it on a different page. You could do your work on a different page too, since there's not much here. I'll have to go past that one. So we all should remember y2 minus y1 over x2 minus x1, right? That's how we find the slope. But our slope, I'm not going to call it m, because it's not a generic slope. Remember, our slope represents velocity, right? So the velocity for this kind of graph is going to be representative of the slope, and I plug in those numbers. 20 minus 0 over 5 minus 0. And we get a velocity of 4. 4 what? What's the units? Look at the graph. What's the units for the position? Meters, right? What's the units for the time? Seconds. Didn't we divide values on the y-axis by values on the x-axis? So that means we divide the units too. So velocity units are meters per second, right? Makes sense? So my velocity, and with 1D motion, you don't have to stress that it's positive. We all know that if we don't make a number negative, we assume it's positive, right? If you really wanted to, you could, but you don't have to. It's clearly a positive slope going uphill. So main point is that this is really, finding slope is really the equation v equals d over t from a week ago, right? We mentioned that yesterday, but it's super important to remember. This equation did not come out of thin air. it actually became y2 minus y1 is actually the displacement, isn't it? Because those were positions, weren't they? The difference between two positions are displacement, right? And the time interval is the difference of x2 and x1, right? 5 seconds minus 0 seconds. That's a total time. So this formula we learned a little while ago, I told you eventually we'd find out where it came from. This is where it came from. It's the slope of a PT graph is what velocity is. Any questions on that? All you got to do to finish up then and turn it in by tomorrow is do the same thing on these 3 remaining ones. Then submit this, please.